So, the first thing we probably need to do when we talk about unique properties of water is we got to go back and talk about why water has unique properties. Okay, so at the end of yesterday's notes, we talked about polarity, right? Molecular polarity and bond polarity. And if you notice, we used water as the example for both types of polarity, both molecular polarity in that it's a bent shape, and bond polarity down here in that each of the bonds is polar. Okay, but that's part of it. The other part is that water has something special. It's called a hydrogen bond. Okay, and hydrogen bonds are, it's a terrible name, first of all, because they're not bonds at all. There's only three types of bonds. There's ionic bonds, covalent bonds, and metallic bonds. And hydrogen bonds are actually intermolecular forces, which means that if you have two water molecules, the way that they interact with each other is through something called hydrogen bonding. And the reason why hydrogen bonding is so special is because it acts like no other element acts. Okay, so if we look here, we said that oxygen takes all of the electrons away from the hydrogen, right? It pulls them away. Okay, most other elements though have other non-shared electrons that'll still be floating out here, right? They'll still be orbiting around, the ones that aren't part of the valence shell, right? So they would still have some electrons out here. But hydrogen just has the one electron and it's got one proton. And so it's only got one shell, one orbital. And when you take that one orbital and you pull it all the way over here, the only thing that's over here now is just a proton, right? It's like a naked proton sitting out on the outside of water. And so it's super, super, super positive. It's the most positive thing. It's a proton, right? Whereas all other molecules that don't have hydrogen bonding are going to have some other electrons out here, so they're not going to be quite as positive. So this is super positive down here. This is the same amount of negatives it would be with any other thing. Okay? So hydrogen bonding exists when you have a compound that forms that has hydrogen in it, obviously, that also has nitrogen, chlorine, or oxygen. Or technically fluorine also, but like we're not going to use any fluorine compounds in here. Okay? So, what does that mean? What does the hydrogen bonding mean? It means that, okay, if I have, here's one water molecule, here is another water molecule, okay? Let's say they're moving around each other and they try to do this. They won't ever interact this way, because if they're interacting this way, this is going to put the positive end of one by the positive end of the other and the negative end of one by the negative end of the other. They don't want that, because opposites are going to attract and like charges are going to repel. So every time that these molecules get close to each other, they're going to orient themselves so that the positive end of one of them is faced up with the negative end of another one, right? And it's so every time two water molecules come past each other, they're always going to sort of tug on each other a little bit to get them to orient in the correct way. Okay? Same thing if you try to pull them apart, right? If you try to take this positive and negative here and try to pull them away from each other, they're not going to be super happy about it. I would say the difference here between non-polar molecules and polar molecules, let's say I had two blocks of wood, right? And I put them on a table, and then I just moved them past each other. They didn't interact anyway. So this would be like non-polar molecules. Now let's say I have two magnets and I put them on a table and I drag them past each other. You're going to feel as they try to orient themselves so that the fields are opposite, so that the positive end of one magnet is going to line up with the negative end of another one. Sometimes that's it'll feel like they're pulling together. Sometimes it'll feel like they're pushing apart. The point is that they're interacting with one another and they're affecting the way that they're acting. Right? That's the idea behind intermolecular forces and the idea behind hydrogen bonds, which are the strongest intermolecular forces. Make sense? Okay, so that's what we can say. Very first thing here is that water is extremely polar and it has hydrogen bonding. Water is very polar and has hydrogen bonding. And so we're going to talk about these unique properties, and really when it comes down to it, all the unique properties that we're going to talk about are the result of the polarity and the hydrogen bonding that water has. Okay? So the first one is probably the most obvious one, and that is that water is a really good solvent. Water is the is a very good solvent. People go so far as to call water the universal solvent. It's not really. It won't dissolve everything, but it dissolves a lot of stuff. And that's why it's really important for us. Because if you look at something like our blood, the main job of our blood is to carry stuff from one part of our body to another part of our body. Well, what's your blood mostly made out of? It's mostly water. Some people say it's mostly red blood cells. That's not true. It's mostly water. And the reason why it has to be mostly water is because the water is needed to carry all the stuff around your body. Because it's a really good solvent. So it's really good at dissolving like salts, like chloride ions and sodium ions and calcium ions, potassium ions. Those are all dissolved in the blood and transported throughout our body, right? Also really good at dissolving covalent compounds as long as they're polar covalent compounds like glucose. Really good at dissolving glucose because it's a polar covalent compound. So the idea here is that we need water to be a good solvent so that it can support life, and that it is a good solvent. Okay. Things that dissolve in water. If you remember from chemistry, we know that polar substances or polar solvents are going to dissolve polar substances and ionic substances, right? So we can say that water can dissolve polar substances and ionic substances. Okay, so the term that they use in chemistry to describe this is miscible, right? So we'd say that those two substances are miscible, meaning they can dissolve. The term that we use in biology, though, is hydrophilic. Okay, and hydrophilic uses a prefix, hydro, which means water, and a suffix, philic, which means the love of. You guys have probably heard this before if you've heard of like necrophilia or pedophilia or something like that, right? That literally means the love of dead things and the love of children, and neither of them are in a positive context. But that's where that suffix comes from. It means the love of water. So these things love water, so they're going to dissolve in it. They're going to want to, get very close to it. Okay. So there's stuff that water can't dissolve, and those things are nonpolar substances. So water cannot dissolve nonpolar substances. And as a result, we refer to those things, again, in chemistry, we would call them immiscible. But in biology, we're going to refer to them as hydrophobic, meaning they are afraid of water. Hydro meaning water, phobic meaning the fear of, right? So because they're afraid of water, they're going to want to try to stay away from it. They're going to want to clump together and not interact with the water. They're going to not dissolve or anything like that. Okay? This is going to come up all year. We're going to say hydrophobic and hydrophilic like at least 5 times a week for the rest of the year. So get familiar with those words, know what they mean. Next interesting property of water. Water is less dense in solid form, which is ice, right, than liquid form. Okay, and I hope that your chemistry teacher talked to you about this, and if they didn't, I just want to take a second and make sure that you get this. So in elementary school and middle school, when they learn states of matter, it's really easy for the teacher to just say, okay, in a solid, the molecules are really close together. And then when they transition from solid phase to liquid phase, the molecules get further apart, right? And then when they go from liquid phase to gas phase, the molecules get further apart. Everybody's heard that, right? That's how they're supposed to teach it. But it's not true, right? Specifically for water, we know that ice, or the solid form, the molecules are further apart than when it's a liquid, when they're closer together, right? So that's very strange. And it results in a lot of behaviors that I'm sure you're aware of. Like if you put ice into a drink, it floats to the top, right? How many other things does that happen in? If you had like, metal or something like that, and it was molten metal, and you took, a big chunk of solid metal and you threw it on the molten metal, it doesn't just stay on top. It'll float, or it'll sink to the bottom because it's going to be more dense, because in that case, the solid is going to be more dense than the liquid. But that's not the case with ice. Okay, this has some other cool implications too, like if you've ever been ice skating. The way that ice skating works is you're on this big sheet of ice, and you've got these blades on your feet, and they're called ice skates, right? And so you step on the ice with the blade, right? And it concentrates your entire weight into a very small space, and so it gets compressed, right? Or the molecules get compressed, and we know that when we compress a solid, we know that when we compress solid ice, the molecules get closer together, which turns it into liquid ice. So that means that directly under your feet, directly under those blades, you're not actually on ice, you're on a very small amount of water that you've made by compressing the ice with a blade, right? That's why you slip. That's why it's nice and skatey, right? You can skate on it. And if you've ever seen like a little kid try to ice skate, it doesn't work. So like, let's say you got hockey parents or something like that, and you're like, oh, our kid's now 2 years old, it's time to get them their first set of skates. And they go out, and they're just like walking around on the ice in their skates. It's not the kid's fault. It's not that they don't know how to ice skate. It's that they don't weigh enough to compress the ice enough to turn it into water, and so it's not slippery under their feet. They're just walking on it like they would if it was carpet, right? Because they're not getting any of that water underneath their blade. Right? The same thing goes when you come off of the water with your ice skate. There's no water behind you, because at that point you're not compressing it anymore, and so it can get nice and spread out again and turn back into ice. Right? Pretty cool, right? Well, how does this have to do anything with biology? Why do we care? Well, if you think about where most living things started, or where we think living things started, it was in the water, and for a long time everything was in the water, right? It took a really long time for stuff to move out of the water. And during that time where stuff was in the water, there were a few ice ages. Okay, so if there were these ice ages, in fact, they weren't even ice ages. They were something that we call snowball Earth, which is like ice age times 100. It's like everything gets covered in ice, whereas in an ice age, not everything is covered in ice. But one of the things that happens is bodies of water form a layer of ice on top of them because the ice doesn't sink, right? And once the body of water forms the ice layer on top, that ice layer insulates the rest of the water from freezing. Okay? If it wasn't the case, if ice was more dense, then what would happen is ice would form on top and it would sink to the bottom, and then ice would form on top and sink to the bottom, ice would form on top, sink to the bottom, sink to the bottom, sink to the bottom, sink to the bottom, and the whole body of water would freeze. And if the whole body of water freezes, everything that was living in it would die. Right? But that's not the case. Right now, when water freezes, it freezes on the surface, and then that surface ice prevents the rest of the body of water from freezing, right? So we can say that surface ice prevents large bodies of water from freezing completely. Which is a good thing, because then all the stuff that's in it doesn't die. Okay. As we said, water has hydrogen bonding, and the thing about hydrogen bonds is every time they go past another molecule, they're going to interact with it in some way. Even if it's a non-polar molecule, they're still going to interact with it in some way due to these forces called London dispersion forces. It's not really important that you know the chemistry behind London dispersion forces. You should just know that like non-polar molecules even are going to have like slightly polar moments called LDFs. Don't worry about it. Just know that hydrogen bonding messes with everything. It messes with all types of molecules. Okay, we can say that hydrogen bonding makes water sticky on a molecular level. Okay, And so this manifests itself in a couple properties. One of them is called adhesion, which basically just means that water will stick to other molecules. So water attracting other or molecules other than water. And then the other one's called cohesion. And the difference between adhesion and cohesion is anything that's not a water molecule, so water sticking to anything other than a water molecule, and then cohesion is water molecules sticking to themselves or sticking to other water molecules. Attracting other water molecules. And this is important in biology for things like transpiration pull in plants, how a plant moves water from its roots to its shoots. It actually does it through a suction force, meaning that it's pulling the water molecules from the top of the tree up. And if they didn't have cohesion, you couldn't do that because you would pull a water molecule up and it wouldn't pull the rest of the water molecules behind it because they wouldn't be sticking together. You would just pull one water molecule up. But if you pull one water molecule up, cohesion allows for the rest of the water molecules to stick together and pull up sort of like a rope or something like that. Okay. The other result of cohesion is surface tension. Surface tension is important for a whole host of bacteria and bugs and things like that. Doesn't have as large of a role in our life, but lots of aquatic organisms rely on surface tension. Let me check when this period ended really quick. It ends at 42, which is 10 minutes. Awesome. The last thing is about something called specific heat and heat of vaporization. So we say that water has a high specific heat and if you remember from chemistry, the term for that is C sub water, or the letter C sub water. C means specific heat, right? And a high heat of vaporization, which again is delta H VAP. Okay, so what do these things mean? Specific heat is the amount of energy required to raise the temperature of water, and it's very high. It's like 4.18 joules per gram degree Celsius. And then it also has a really high heat of vaporization. I think it's like 40.7 kilojoules per mole at 100 degrees Celsius, right? But much higher than everything else is the point that I'm trying to make here, okay? So if we first talk about the specific heat, Tampa's a very nice place. I love living in Tampa. One of the reasons why I love living in Tampa is that the temperature is very consistent, not only from day to day, but also from daytime to nighttime, right? So let's say I want to go out and see a movie, and in the course of seeing a movie, it transitions from daytime to nighttime. So I walk in to the movie theater and maybe it's like, I don't know, 95 degrees, and then I walk out of the movie theater and maybe it's like 88 degrees or something like that. There's not a huge temperature swing, okay? If you compare this to some other place, like let's say we go to Vegas, right? In the daytime in Vegas, it can be like 115, 120 degrees, right? Whereas the same time at night, so it's 120 degrees during the day, and then at night it might drop down to like 80 or even 75, right? So we're talking about huge temperature swings, 50 degrees temperature swings here. And the reason for that is that in Tampa, we're surrounded by bodies of water. We have Tampa Bay on one side, and we've got the Gulf of Mexico on the other side, right? But in Vegas, there's really not a whole lot of water. There's like the Hoover Dam and Lake Mead there, but that's really it. So there's mostly just desert other than that. So that means that sand, which is mostly the stuff that's in the desert over there, must have a very low specific heat. It does. We said that water was like 4.18 joules per gram degree Celsius. Sand is like 0.8, right? So a lot more energy to heat up water, and a lot more energy gets given off as water loses heat. That means that during the day, water cools us down, it acts as a heat sink, and during the night, it acts as a heat source. And you can easily figure this out or see this by going to the beach. If you go to the beach during the daytime, the breeze that's coming in off the ocean feels cool, and if you go to the beach at the nighttime, the breeze that's coming in off the ocean feels warm, because it is. It's warmer than the air that's by the sand. Right? Because it's giving off heat because it has a higher specific heat. Okay? This is really important not only for the fact that it's going to regulate ecosystems, right? But it's also going to regulate our bodies. Our bodies are mostly water, right? And so it takes a lot of energy to heat our bodies up and cool our bodies down, which is a good thing because we don't want our bodies swinging in temperature a whole bunch, right? So we can say that water regulates temperature by acting as a heat source in cool weather and a heat sink in warm weather. Okay, well, let's say that it's warm weather and my body's heating up. I get up to like 100 degrees, right? What's my body do? It's like we're too hot. What do? Sweat, okay? Sweating is water, right? I sweat water. And I want to show you guys something really quick. We're going to do a quick example. Here, can I borrow your hands? Just go like this, okay? In this hand, I'm going to put water. This is just water out of the tap, okay? And in this hand, I'm going to put some hand sanitizer. This is ethyl alcohol. All right, so let them air out for a second, and then tell me which one feels cooler. The ethyl alcohol does, right? Which is weird because I just told you how good water was. You can rub your hands together. I just told you how good water was at cooling. Well, it's not that water's better at cooling, it's that it's more efficient at cooling. The ethyl alcohol has a really low heat of vaporization, so it vaporizes immediately, right? That's why you can put some on your hands and do this, and then they're dry, right? And as it vaporizes, it takes all this energy away from you, right? It takes energy to vaporize something. Okay, but the problem is if we were made up of ethyl alcohol instead of water, or if you sweat ethyl alcohol instead of water, instead of having to drink 8 cups of water a day, you would drink something like, I don't know, 7 gallons of ethyl alcohol in order to get the same amount of cooling, right? And believe me, if you drink 7 gallons of ethyl alcohol, you will indeed die before you cool yourself off. So I wouldn't do that. And the reason why it's more efficient is because it's a high heat of vaporization. Sure, it takes longer for it to evaporate away, but as it evaporates, it takes much more energy with it every time it does evaporate, right? So we can say that water is an efficient evaporative cooler because of its high delta H VAP. Again, so this is like, it's 40.7 kilojoules per mole at 100 degrees Celsius. But your body doesn't get to 100 degrees Celsius, I hope. That would be bad. That'd be 212 degrees Fahrenheit, and you'd be very, very dead. So at body temperature, it's even more than that. It's significantly higher. It takes a whole bunch of energy to vaporize water at body temperature. And so every time it vaporizes, it takes a tremendous amount of energy away from you. The reason why you might want to like wipe off sweat to allow it to vaporize is because if you imagine that all of the water around you or all the water that's on you is got that high specific heat, if just the surface level is vaporizing, then it has to change the temperature of all of the water that's also on you. So if you wipe off a lot of sweat, like if you're just dripping in sweat and you wipe it off, you will in fact cool down faster because now you don't have to change the temperature of the sweat that's there, right? You just change the temperature of the skin underneath and the body underneath that. Make sense? Anybody have questions? That's it. You guys can chat.